So I would like to thank the organizers for giving me this opportunity to give a talk. Eduardo and Lothar and Klaus, and one of them is actually here, so thank you. This is a conference about moduli spaces. So let me introduce 3 moduli spaces that will appear in this talk. The first of them will be the main topic, and 2 more are auxiliary. So AG is the moduli of abelian varieties of dimension G. And I only look at principally polarized. And so this is a quasi-projective variety of dimension G times G plus 1 over 2. MG, as usual, is the moduli of curves of genus G. This is a quasi-projective variety of dimension 3G minus 3. RG parameterizes such curves together with the non-zero 2 torsion point. So n is not 0. Eta is not 0, but 2 eta is 0, a 2 torsion point. And so for any such 2 torsion point, you have étale 2-to-1 cover, 2-to-1 cover. And on this cover, you have an involution, iota. This is a curve of genus G. This is a curve of genus 2G minus 1. And there is an obvious forgetful map, and just forget the 2 torsion point. It's a finite map. Therefore, this variety also has dimension 3G minus 3. And then there are some standard maps between these spaces. So we have the Torelli map. So Torelli map from MG to AG, where a curve goes to its Jacobian. And then there is also another well-known map, which is Prim-Torelli. That goes from RG plus 1 to AG. What it sends, it sends this pair, so that's the same as the pair C tilde and iota. This sends to the Prim variety of that pair, and by definition, you look at the Jacobian of this curve C tilde, and you look at the -1 eigenspace of the involution. So you have an involution, you have a plus space, +1 eigenspace, -1 eigenspace, you take the -1 eigenspace, and you get an abelian variety of dimension, which is the difference. So that's why it goes from G plus 1 to G. So this eigenspace, you can define, you can say it's the kernel of 1 plus iota, and then take the connected component of identity, or you can say it's the image of 1 minus iota. That will also do. Okay. So these are the basic spaces. Now, as I said, mostly I want to talk about AG. And so let's recall what is known about the birational type and Kodaira dimension of AG. The results are as follows. So for G less or equal than 5, this Kodaira dimension kappa is minus infinity, and moreover AG is unirational. For G starting with 7, this Kodaira dimension is maximal possible, so dimension of AG. So this is the variety AG is of general type. Let me maybe briefly remind the definition of this Kodaira dimension. So you take AG and you pick something birational isomorphic to it, but smooth and projective, so a smooth projective model, and then you look at how many pluricanonical sections it has as n grows. So as n goes to plus infinity, and this grows as n to some power. And so this power is called the Kodaira dimension. And so Kodaira dimension minus infinity means that all of these numbers are 0. So this is what's been known for a long time. I will remind a little bit about these cases, and I'll say who proved what. But so this is an interesting case. So that's has been an open case for 40 years, 45 years. Yeah. That's the case I'd like to talk about today. So let's start with the known cases, though. So there are two opposites here, and the proofs in these two opposite cases are very different by very different methods. So for G greater or equal than 7, this was proved by Mumford in 1977, and proved as follows. Here's the main idea. So you start with AG, and of course AG is not compact. And so to compute the Kodaira dimension, to compute some numbers like that, you want to pick a compactification. And there is a partial compactification. So this is partial compactification AG star, where you only add one divisor on the boundary, the simplest degenerations of abelian varieties. So as abelian variety degenerates, it splits sort of in a lower dimensional abelian variety and a multiplicative torus. So here the dimension of this multiplicative torus is 1. So there are rank 1 degenerations. So this is still not a compact type, not a compact variety. However, there is a theorem of Thai which says that if you have a pluricanonical form here, then it extends to any toroidal compactification. And so therefore, you can actually, for these purposes, for computing pluricanonical forms, you can just work on this non-compact variety. And the Picard of this variety is two-dimensional. It's generated by two generators by the Hodge class. So this is Hodge class, mentioned several times already in this conference, and then you added a divisor, so that D. And the Hodge class is big in this sense, that if you look at a big multiple and look at the sections, then it grows maximally. So what you want to do, you want to write the canonical class of this partial compactification as something effective plus a little multiple of this lambda. And alpha, so just anything but positive. And that will do it. because then sections here there are at least as many as for lambda, and it's of general type. Now the formula, Mumford gave the formula for the canonical class of this AG bar, AG star, and it's just G plus 1 lambda minus D. And so then all you want is you want to find an effective divisor here so that you can plug into this formula. Just would be slightly smaller than this with respect to lambda. And so what are divisors on the moduli of a space of abelian varieties? One very obvious divisor is called N0. This is those abelian varieties such that the singular locus is non-empty. So it's a divisorial condition for the theta divisor to acquire a point. And Mumford computed explicitly this, so there's some formula depending on G in this basis. So there's some explicit formula, which I will not write. But the upshot is that you plug it into this formula, and you see that it works precisely when G, starting with G equals 7. And you're done. And so then,
so the effective divisor is N0?
Yeah, N0. So some multiple of N0. That's it. So, and the game is over. So that's this case. Now for G lesser or equal than 5, the game is the opposite game. So what the varieties are unirational, and the way it's proved is you dominate it by some other, maybe easier unirational varieties. And of course, this is what you do. So you use these maps. And so the Torelli map, MG to AG, this is dominant for G up to 3. And the Prim-Torelli map, this is dominant for G up to 5. And so therefore, so you just prove that these moduli spaces are unirational. And the whole point of this story is that the moduli of curves are much easier than the moduli of abelian varieties. Of course, the moduli of abelian varieties is a quotient of a symmetric domain by an arithmetic group. But a general abelian variety is a very mysterious thing. But curves are one-dimensional objects, and it's much easier to parameterize them. Maybe you look at some covers, and so they're given by ramification points. Curves are easier, and so these spaces are much easier to understand. And so the hardest case here was R6, right, which dominates A5, and so this space is unirational. And so this was proved by Donagi, Mori-Mukai, and Vera at about the same time, 83, 84, within several months of each other. So that was the first proof. Published version is not always the same as when it was proved, but I think Donagi proved it first, but then I think Vera's proof is the easiest to understand and the nicest. And so therefore, A5 is unirational. And so the question is, what about genus 6? So there will be two parts to my talk. The first part will be uniformization of A6, also known as Kaniev's conjecture. And then the second part will be consequences for birational type of A6. So Kaniev proposed a way of parameterizing A6 by curves with some extra structure. So which is quite similar to this picture. So here we just uniformize abelian varieties by curves, here by curves with involution. And in Kaniev's construction, it's curves with some extra structure. And this is an old story. I think when I was a student at the end of 80s, I heard him talk about that. And so, and this, he gave this conjecture in some talk in Moscow. And yeah, he's been giving these talks at other universities as well. This construction also appears in papers by Lange and other people. So let me tell you what the construction is about. So you start with a very classical story. You start with a cubic surface in P3. And so as everybody knows, on a cubic surface there are 27 lines. Okay? And so you represent these lines by points. So there are 27 points. And then let's now vary this cubic surface. So let's start with the cubic threefold now. And look at a pencil of hyperplane sections. So cut it by a pencil. Now on every surface in this pencil you have 27 lines, and so what you have is down there is your pencil, P1, and you have a 27 to 1 cover. And so this is, let's call this curve C. So there is pi, and it's 27 to 1. Now, sometimes this threefold degenerates, and for a generic Lefschetz pencil, you can assume that the degenerations are the easiest, where a threefold acquires a single node, a single quadratic singularity. And then what happens at such points, that's very easy to compute. There is a ramification of this sort. So there are 6 simplest points of ramification, and then there are 15 sheets where there is no ramification. And so that adds up to 27. And so that's a ramification point here. Let's call it Pi. And the number of such ramification points, again, that's a simple computation. There are 24 such ramification points. So on a threefold, that's your threefold, you now have a singularity, and what happens is 6 pairs of lines come together, and they pass through this point. So that's a point of multiplicity 2. You intersect with a threefold. These lines are intersection of a quadric and a cubic. So it has degree 6. So there are 6 pairs of lines. So these distinct lines come together. So there is now they're identified of multiplicity 2. Why? Well, what? You know, there were 27 lines, and now some of them now in pairs. They come together. So that's, a fiber now has 6 points of multiplicity 2. All right, so now on the base, let me draw this. This is the CP1. You have 24 points. And a cover like that, so outside of these points, the cover is unramified. And so such a cover is given by some datum of monodromy. So there are these local monodromy, W1, W2, etc., W4. And they generate some subgroup of S27, because this local monodromy is exchange. They act as reflections on these 6 pairs of sheets. So one can compute that this group is the while group of the E6 lattice. So it's WE6, a reflection group, and these W's are reflections. So of course E6 is intimately related to the cubic surface, as classically very well known. Okay, so that's the picture. So what kind of adds to this picture? There is a correspondence. He adds a correspondence B in C cross C, and then we have 2 projections: first projection, a second projection. So what is that correspondence? So a point L prime is in B if and only if the following happens. These things are lines on a surface. So these are lines on some surface ST in this pencil. And so you say that they're in a correspondence if these lines intersect at a single point. And so on a cubic surface, every line intersects 10 other lines. And so therefore, this is a map of degree 10, and this is a map of degree 10. And when you have a correspondence, that gives you an endomorphism from the Jacobian of this curve to itself. So this is peak 0. Works as follows. So you start with some invertible sheaf here, and you pull back, and then you push forward. And so, but you push forward on. This is the norm map. So you push forward as divisors. So you have an endomorphism, and so kind of prove that this endomorphism of the Jacobian satisfies the following equation, the following quadratic equation. And in a situation like that, you have what's called the Prim-Turin. Really, it should be called the Kanev variety, but he called them the Prim-Turin varieties. And this is the -5 eigenspace of that Jacobian. So you have a +1 eigenspace and a -5 eigenspace. And you define that as before, as for usual. As for prim varieties, you can look at the kernel of D+5 and look at the connected component of identity, or you can look at the image of D-1, and then you don't have to take the connected component of the identity. So that's a prime-Turing variety, and let me put this theorem again of Konev. So here, which says that in this situation, this prime-Turing variety is a principally polarized abelian variety of dimension 6. So you get some principally polarized abelian 6-folds this way. Well, that's the construction. So let's look at what we have. So we have these covers C2P1 coming from pencils of on cubic 3-folds. Let's call this space T. And we have a prime-Turing map to A6. Now, A6, by the formula, it has dimension 21. These pencils on cubic 3-folds, of course, very easy to compute. You know how many cubic 3-folds you have, and you add a pencil. This has dimension 16. But worse than that, you can compute this map. This is an easy map. So a pencil like that goes to the intermediate Jacobian of this cubic 3-fold, which is a principally polarized 5-fold, plus an elliptic curve. And this elliptic curve is the base locus of that pencil. It's a cubic curve. That's the base pencil of base curve of that pencil. So you only get A5 plus A1 inside of A6. So the image really, it goes to A5 cross A1 in here, and that space has dimension 11. So certainly you cannot uniformize an arbitrary abelian 6-fold this way. However, you do the following. So you look at all covers pi from C to pi 1, which are of degree 27, which are ramified at 24 points, such that the global monodromy group is WE6, and local monodromy, there are reflections. So you look at all covers of this form. You don't care if they come from cubic 3-folds. You just look at all of them. So that's a Hurwitz scheme, parameterizing curves with an extra data, ramification data. And you still have this prime-Turing map defined the same way, because you still have this correspondence. If you vary this curve a little bit, this cover a little bit, you still can, in a local neighborhood, you can still distinguish, these fibers as lines. So you still, this is still well defined. And even if you go far away, so you change things by a monodromy, but this monodromy is WE6. And this monodromy is this group acts by reflections. So it preserves these products. And so this condition is, this correspondence is well defined for any such cover. So there is still the prime-Turing map. You look at covers like that, 27 to 1, has 24 ramification points. They're all of this form. They're all of this form. So this WE6 naturally sits in here. It as permutes the 27 lines on some fixed cubic surface. And so you just require that the local monodromy around one point should be like that. And, but globally, they should generate WE6. That's a Hurwitz scheme. It is irreducible. That's another theorem of Konev. Now, what about the dimension of this space? Now, there is an obvious map here which goes to M024, forget the order. And so this map is, it just forgets these local monodromy elements, but just keeps the points. So on a P1, you have 24 points. Now that's obviously an étale map of finite degree. You're forgetting some finite data. You're just forgetting these WIs. So it's a finite map. So the dimensions here are the same. And the dimension of M024 is 21. So now you have a very suggestive map between two varieties of the same dimension, 21. And so a conjecture of Konev is that this map is dominant. And therefore, you can parameterize your abelian sixfolds by curves with extra data in this way. And so you can consider this Hurwitz scheme to be like a master space for all abelian sixfolds. And this is an old conjecture, so from at least 1980s, mentioned in some published papers, etc. Okay, so the theorem for part one of this talk is that this conjecture is true. And so that's what I'm going to talk about next. And for the proof, I will use degenerations of prime Turing varieties. So prime Turing varieties. But of course, this story is a generalization of the older story, so you need to understand the degenerations of Jacobians and then of prime varieties, and then maybe you can understand the degenerations of prime Turing varieties. And so when you study degenerations of Jacobians, then all these interesting questions appear. You want to study maybe compactifications of generalized Jacobians. So, however, that's not what's needed, or that's not what we use in this proof. We use just some formulas for I need to know how the Torelli map degenerates. There is a formula for the Torelli map. I need to know how it behaves near the boundary. And so for what I need, for Jacobians, this was done by Namikawa in 74. And for prime varieties, we did it with Birkenhacke and Hulek. When did we do it? I don't remember. So maybe 2002, I don't remember. And so this part is new, right? But very much by analogy, so maybe not so new. So once you understand this case, then maybe this follows very easily. So let me go ahead and start with the Jacobians. So here's the situation. So you start with mg bar, and in mg bar you pick a point. So you pick a point of maximal degeneration. And you pick some open neighborhood. And so you can model this neighborhood on a neighborhood of C 3G minus 3. So it looks like this. So there's that's your U, sitting in 3G minus 3. Then there are 3G minus 3 divisors given by just equation zi equals 0. So I is from 1 to 3G minus 3. So 3G minus 3 of them. And this point represents a curve in mg bar, which is maximally degenerate. So this curve then is this curve. I see is the union. It's glued from p1s. There are 2g minus 2 p1s, and you can associate to that a dual graph gamma. It's trivalent, so here's the simplest case maybe when your curve is a $sign curve, yeah? And the graph is this graph. That's gamma, that's C. And this is a curve of genus 2. Okay. So, and in this situation, now from MG, you have a map to, well, you have a map to AG, but AG is a quotient of the Siegel upper half plane by this arithmetic group. So, and a point in here is represented by a matrix G by G, complex matrix. It is symmetric, and the imaginary part is positive definite. And this map is, of course, multivalued. So before, map to AG is single valued, but when you lift it in this neighborhood, then it's a multivalued map. And Namikawa, in his PhD thesis, really, wrote this formula, explicit formula for this Torelli map near the boundary, near the maximal degeneration point, and it looks like this. So f of z1, etc., z3g minus 3 is the sum of logarithms of zi over 2 pi square root minus identity times some monodromy matrices plus a holomorphic function. And now MIs here are some G by G, symmetric G by G matrices, integral valued. So further you can apply the exponential map. So exp of 2 pi square root of 1 something, and that will model this map. So that will be locally, that will be a model for this map near the boundary. And so then this will go to some products of monomials like this, yeah, U to MI, and then times something bounded holomorphic. And so the point of this story is that the map from mg bar to ag bar near the boundary is monomial, essentially monomial, given by these monomials. So it becomes toroidal up to some bounded holomorphic function. Yeah, it can be interpreted as the statements on the limiting, exactly. So Hodge structures are the elements of AG, of Hodge structures of weight 1. Okay, but moreover, these matrices are completely explicit. And I want to tell you what they are. So you have this dual graph gamma. And you look at first homology of this graph. In this case, it's z squared. So these are loops here. And now for every edge, EI, you have EI star, which is a linear function on this space. And the usual linear function, EI star on EJ, is the Kronecker symbol delta IJ. So it equals 1 on EI, 0 everywhere else. This is a linear function on this G-dimensional lattice. And MIs are just squares of these linear functions. So a square represents a symmetric G by G matrix of rank 1. That's what they are. So, but what does that give you? So you see Torelli map is a complicated transcendental map, hard to study. But near the boundary, this is the leading term. So this grows fast. And this is, that's a holomorphic function. This goes to infinity. So if you only are interested in some rough properties of this map, such as dominance, then you can ignore this term. You can just look at this leading term. And as an example of this, let me prove a weak Torelli theorem for you, which may look funny, but it will perfectly illustrate what I'm going to do next for prime-Turing varieties to prove this kind of conjecture. So I will, as an sample lemma, I will prove that the dimension of the image of MG to AG is 3G minus 3. So that's stupid in a way that, of course, by classical Torelli, this is an embedding. But I'm going to prove it with these combinatorial methods by using graphs and those monodermy matrices. So all I need is these 3G minus 3 matrices, EI or quadratic forms, EI star squared on H1 of gamma Z to be linearly independent. That's all I need. If they're linearly independent, then just looking at the principal part of this formula, you see that the image has dimension 3G minus 3. There are 3G minus 3 things that go to infinity independently, and this you can ignore. And by graph, so some combinatorics, combinatorics, you can prove that this is a statement about graphs, right? So you can prove that this is equivalent to saying that this graph, gamma, is 3-edge connected. Maybe I'll tell you which graphs are not edge connected. So a graph that has a disconnected edge is not two connected. And a graph that has of this form, where you can split into two parts and there are only two bridges between them, that's not 3 connected. And so 3 connected is when this doesn't happen and this doesn't happen. So when you cannot split it into two parts which are only connected by one bridge or two bridges. And that's all. So if you have a graph, Oh, the dualizing line bundle for any stable curve is ample. It's very ample. Oh, maybe I don't remember it. Yeah, it's not important here, but I actually don't remember it. So, but anyhow, now from graph theory, you know that such graphs exist in every genus. Well, so you're done. So that's the proof. So what do we need to prove this theorem about the dominance? Well, the idea is, but before I go to prime-Turing, maybe I should briefly say about prime varieties. So what are the monodromy matrices for primes, for ordinary primes? So in the prime situation, you have a double cover. It's a tau. And then you have an involution here, iota acting. And so on the first homology, so this could be stable curves. And so there is this graph for C tilde. And on this first homology, now you have an involution acting. And so the monodromy matrices are just this. So you compute this E star squared as before. And then you restrict it to the -1 eigenspace for this action. And that's it. And so using this, you can prove some theorems about primes now, if you like, including some classical results. But, well, given this, now what are the monodromy matrices for prime-Turing varieties? Well, in this situation, you have this curve C, which has this 27-to-1 map. Yep. Yes. There is a formula just like that, I'm saying. There is just like that, only MIs are now different. Again, there is a leading term, like this, and I'm telling you what these matrices are, and that's what they are. And for prime-Turing varieties, so what I'm going to do, so we start with this cover. The genus of this curve is 46, pretty high, and there is a map, 27-to-1, and then there is this correspondence, right, in C cross C. And what I'm going to do, I'm going to generate, so downstairs I have this P1 and P24, which are points here. And what I'm going to do, I'm going to degenerate to a point of maximal degeneration point in M024 bar. Yeah. And then this curve also will degenerate, but I can compute it. It will be also a union of P1s, so it will also correspond to some very large graph. Now on the first homology of this graph, there will be an induced endomorphism, and this endomorphism satisfies, I'd like to say it satisfies this equation, d minus 1, d plus 5. But you see that equation only was satisfied not on peak r, but on peak 0. So on the degree 0 part of this homology group, the induced endomorphism satisfies this equation. And then the matrices are the endomorphic, the monodromy matrices are, you just restrict those quadratic forms to that -5 eigenspace. So the thing is now completely explicit. So there is an explicit formula. And for the input for what you want is this gamma trivalent graph, a tree with 24 ends. So it really doesn't matter which one you pick. For example, you can pick a tree like this, if you like, 24 ends. And then for every end, you have this local monodromy. So you have W1, W2, etc., W4. That's the input. The output, you have 21 matrices MI in symmetric 6 by 6 symmetric. And so the dimension here, the rank of this lattice is also 21. And so you have 21 matrices in a 21-dimensional vector space. And now if these matrices are linearly independent, then by the same argument, the map is dominant near the boundary. Because you just look at the leading term, you can ignore the complicated. So the leading term of Torelli, and therefore of prim Torelli, is easy. That's the proof. So now, that's your input, and that's your output. So this step is completely straightforward, just some linear algebra that may be hard to do by hands. So, I wrote a little Mathematica program, and I put some random W's, and it gave me rank 11. Then I tried others, and it gave me a low rank. And then I just programmed it to put some random roots and ran it for half an hour, and it found some cases where the matrices are linearly independent. So that concludes the proof of the dominance. I have only little time to talk about the consequences for the birational type of A6. So for A6. So here's a diagram now that we have. So there is A6, there is this prim Torelli map, there is this Hurwitz space. Now the Hurwitz space is here the points are unordered, so you can also order them. And then this will map to M024, this will map to M024 modulo S24. And so you have a diagram like this. And you want to conclude something about the canonical class of this AG. So, of course, you can pull back this canonical class, and it will be the same as canonical class of Hurwitz minus the ramification divisor. And then you can go to compactifications. And here, as before, really it's sufficient to work over this partial compactification of A6. Right. So this gives, in principle, this gives you a handle on this. So you want to know if this divisor here is big. So you want to know what the ramification divisors are, and then you want to study the canonical class here by using this map. So that's a Hurwitz, this Hurwitz scheme has a projection to M024 bar, and so you want to know, what is the ramification of this? Of this, right? It's the degree is the number of such collections W1 to W24, such that the product of WIs is 1, and they generate WE6. Yeah, it's a very large number, as you can see from here. So this is a group of degree 5,000 something, I think. And so, of course, there are lots of such choices. But, you can still analyze the types, etc. So, okay. So we know most of the things in this diagram. We know what the ramification locus of this map is. We know what the ramification loci here are. We know how the canonical class is pull back and push forward. And at the moment, the only clear statement that we can make is this. The canonical class of that compactified Hurwitz scheme is big. And so that does not imply anything about a 6 right away. So if it was negative, if it minus k was ample or something, then that would imply immediately that the Kodaira dimension here is negative infinity. But it's not. So it's big, and so more work is needed. And so, for example, if we knew, so this is a map of some big degree, which we also don't know. But if we knew just the ratio between the degree of this map and the degree of the ramification, then that could imply that maybe we could conclude that this is also big, and that a 6 of general type is of general type. All right. So anyhow, so we worked. The dominance theorem was proved 3-4 years ago, and but we kind of kept it to ourselves because we tried to compute this guy, but I think we're going to post the preprint next week, maybe, so you will see it.